over there. Now, have you gone through whatever we have done yesterday? Because the concept of channel pinch off is very, very important. Okay, so I would like to just have this concept explained from a slightly different point of view. So here we go. So first of all, we have let the MOSFET be operated at constant overdrive voltage called as VOV. Now, what is this VOV? Let us see that VOV in little bit more details, because this is a new term for all of you. VOV is nothing but VGS minus VT. Now, all of you know that VGS, when it approaches VT, when VGS is greater than VT, then we have the channel formed and then the current starts flowing. This is one very important consideration. So whatever is the voltage exceeding this VGS minus VT. So if VGS minus VT is equal to 0, it simply means VGS is equal to VT. So whatever is the voltage exceeding this VT, okay, whatever is the value of VGS exceeding VT is called as the overdrive voltage. We are going to make use of this overdrive voltage quite often. Okay. Have you understood the concept of overdrive voltage? It's very simple. Yes? Guys? Students? Respond please. Guys, am I audible? Guys?
Yes, sir.
So, have you understood the concept of overdrive voltage? It is simply VOV is nothing but VGS minus VT. Okay? Which in fact is the voltage VDS. So, whenever you apply VDS, so this value VDS, if it is greater than VGS minus VT. Okay, so whatever is the component, so when VDS is equal to VGS minus VT, there is one point, and then we will see in more details about the characteristics. So it doesn't matter right now. So when overdrive voltage is kept at a constant voltage, it simply means that my VGS is greater than VT by some amount. Are you getting this? So I'm just applying VGS, which is slightly or maybe a little bit greater than VT. So this is VGS minus VT, which is nothing but the VOV, and I'm applying VOV over here. Okay, that is what is meant by whatever we said. Okay, now VDS, look at VDS. It appears as a voltage drop. We have seen this from a different perspective yesterday. Across the length of the channel, okay, and if we travel from source to drain along the channel, the voltage which is measured relative to or with respect to source. What does it happen? What has happened? What happens to the voltage along the channel if we travel from source to drain? We have seen that effect yesterday, somewhere here. So if I go from source to drain, what will happen to the voltage? If I travel from source, I'm going here like this towards the drain. So what is going to happen to the voltages at various points? Whether it increases or decreases?
Increases.
It increases. Very good. So the voltage measured with respect to source increases. With increase from 0 to the entire value VDS. So I can say that the voltage between gate and the points along the channel decreases from, what is it decrease from? Earlier, what was the voltage between the gate and the source? What was the voltage between the gate and the source? VGS, which was equal to how much? VGS, use this equation. So if VOV is VGS minus VT, then I find out VGS as what? What is that VGS value?
VOV plus VT.
VT plus VOV. All right. Is that okay? So VGS was VT
Yes, sir.
plus VOV. And this value of voltage decreases from source point, that is from this. So this is at source end. What is the new value at the extreme end? That is at the drain end. What is the value of VGS? It will be this VGD, which is equal to VGS minus VDS. Remember, we are now going towards the drain end, which is nothing but VT plus VOV minus VDS. See this factor. So as this VDS goes on increasing, as I go towards the drain, this VDS increases. So naturally, this value, total value, will decrease. That is what I meant when I said that the channel voltage basically increases from 0 to VDS. Okay. Now, since the channel depth is or depends on this voltage. And specifically, exceeds Vt. Okay. So because of that, the channel depth is no longer uniform. So channel depth is no longer uniform. Okay. So that is the reason why we have the channel length which is tapering, as you can see here, which is tapering towards the drain end. Okay, is that fine? Have you understood this?
Yes, sir.
Okay. Now if I put it this in other form as a graph, you will soon see a very interesting thing happening. So if I mark this point as VGS, so this is the VGS value. Again here it is related to the length of the channel. So here I have L. This again is X in X direction. Okay. So what we have is the voltage drop goes on increasing like this. So this is the increase in the voltage drop along the channel. All right. And the value over here this happens to be the VGT. All right. This happens to be your VDS. And that is the reason why we have a peculiar nature of the channel. So let me draw it. Like this. So this is how the channel will be formed. This depth is proportional to BOV, whereas at this end, this is proportional to BOV minus VDS. All right, is that fine? So this is another way in which I can explain the pinch off effect. Any doubts, any questions with this? Guys? Guys, am I audible?
Yes, sir.
Okay, so let us get back to our previous discussion of, okay, now we have the pinch off being explained and all that. So ultimately, what kind of picture do I have? Just a moment. I'm getting the figure. So this is the kind of scenario that you're going to have. All right. What does this purple area indicate, by the way, just to get you back in the discussion? What does this purple area indicate?
It's a depletion region.
Yes, it is a depletion region surrounding the entire channel. Okay. So you can see that the channel is formed, but the shape of the channel is tapering like this. All right. So we already have seen the why this pinch off effect is there. Now applying KVL to the terminal voltages of the MOSFET, we get VDG or VGD, whatever you like, is VDS minus VGS. See if you understand this. Simple. Whatever is the voltage VDS minus VGS, because you can see here I'm applying simply the KVL. All right. Now if VGS is fixed at some value, say 8 volts, and VDS is increased from say 2 volts to 5 volts, the voltage VDG will increase from guys simple
Yes,
math,
sir.
simple
Yes,
math.
sir.
So what will be the value if VDS increases from 2 volts to 5 volts? What will happen to VDG? What will be the range? VDG will increase from, yes, minus 6 volts to minus 3 volts. This is interesting. How? Simply put the values. VDG when VDS was 2 volts and VGS was 8 volts. This gives me minus 6 volts. Similarly, VDG 5 volts minus 8 volts gives me minus 3 volts. So the range of VDG will increase from. Now why do I say it increase? Because it moves in the positive direction. So minus 6 volts is less than minus 3 volts technically. Okay? Because it is more negative. Alright? So voltage VDG will increase from minus 6 volts to minus 3 volts, and gate will become less and less positive with respect to drain. See if you understand this. Or if you put it this way, VDG is minus 6 volts. It means gate is plus 6 volts higher than drain. Remember, this is VDG. It is not VGD. Are you understanding this, guys?
Yes, sir.
Sure. Are you sure about this? Gate will
Yes,
become
sir.
less positive.
Yes, sir.
Because
Yes, sir.
minus 6 volts means gate is plus 6 volts higher than drain. That is the reason why we are having this negative sign. So it will become less and less positive. Similarly, VDG is minus 3 volts means gate is, yes, plus 3 volts higher than drain. So you can see that because of this increase in VDS, my gate is becoming more and more less positive, or less and less positive with respect to drain. So we can say that gate is less positive with respect to drain. Now because of this reduction in gate to drain voltage will reduce what? The attractive forces for free carriers in the induced channel, causing reduction in effective channel width. Eventually, the channel will be reduced to 0 and the saturation condition is established. By the way, this is the third way or the third method I am trying to explain the same thing, and that is the pinch off. We have seen this pinch off phenomenon from 3 different perspectives. I am talking about the same thing. Are you getting this? So for those who have not understood the previous two, this should be a very easy way of understanding the pinch off. Clear? Is this okay, guys?
Yes, sir.
So we have
Yes, sir.
three different ways in which I can explain pinch off. Very good. So I hope you have understood the pinch off by this time. Okay. Now it's time for us to see how the output characteristic look like. Okay. We'll first look at the output characteristics and then go back to the input characteristics, the transfer characteristics. Just let me copy the characteristics here. So how do the input and rather the transfer and the output characteristics look like? This is what is our topic now. I hope the picture is clear. Yes. Look at the output characteristics first. Look at the output characteristics. Let us say the VT is 2 volts. For the device, the VT is 2 volts. It simply means that after 2 volts, it will start conducting in a particular way. All right. So how does the characteristics, output characteristic look like? Output characteristics means drain current versus drain source voltage. So at VGS equal to VT, which is equal to 2 volts, you see that there is literally no current flowing over here. The drain current is 0. Even if I increase the value of VGS. All right. Is that okay? Now when VGS is 3 volts, if VGS is 3 volts, what is VOV? What is VOV? VGS minus VT. What was our VT? Guys?
2 volts. 2 volts.
So,
This is VOV is
V minus 2.
1 volt. So at that particular condition, you can see that the current is now it has started flowing and it will be constant after a certain point. Now it is better to explain it with this. So where is it constant? Where is it becoming constant? Okay. We'll see that later on. But these are the types, these are the curves that we see. So at this point, you can see that there is a point at which the current saturates different values of VGS. All right. So this is the, let us say, if I try to draw a curve through these points, I will get a locus of all these points in a particular shape. All right. So for a device with VGS equal to 8 volts, the topmost curve, this one. saturation occurs at a level of VDS equal to 6 volts. So you can see here. Now, I hope this is in tune. So, okay. So just a slight change over here, but doesn't matter really. So actually, I think it has already started here. So, okay. So the saturation will start happening at 6 volts. Yes, somewhere. Okay. So saturation has started happening here. Saturation means what? Why is this acting up? Okay. So the saturation has started. Something is wrong here. Okay, approximately like this. Guys, are you able to see that?
Sir, screen is not visible.
One second. Now, so what has happened is at VDS equal to 6 volts, saturation will start occurring. In fact, VD sat, it is called as VD sat point, is nothing but VGS minus VT. So, for a fixed value of VT, the higher value, higher level of VGS, the greater is level. Are you getting this? So at higher the value of VGS, higher the value of VGS, I'll get the saturation at a higher point, and that is the reason why you see it saturates here very early for VGS equal to plus 4, let us say. So saturation will start at VDS or VDSAT will be simply 2 volts. Here it will be 5 minus 2, that is 3 volts, and so on and so forth. So that is the reason why you get a peculiar characteristic of the curve like this. Again, for values of VGS less than VT. What is the situation? For values of VGS less than VT. What is the situation? VGS less than or equal to VT. You see that there is no drain current flowing at all. So ID is equal to 0 there. These characteristics show that as VGS increases, from VT to 8 volts, the saturating level or saturation voltage or saturating voltage for ID also increases from, so saturation level, that is ID, also increases from 0 milliamperes to whatever is the maximum value here, 10 milliamperes. Or in simple plain words, what can I say? VGS controls ID. Very important. Why is there a saturation like this? Again, let me see whether you have understood. Guys, why this saturation happens? Saturation of drain current, why does it happen? Quick check. Guys, are you there with me?
Sir, it reaches the pinch of voltage.
Yes, sir.
It is because of?
So it reaches the pinch of voltage.
Yes, it is because of the pinch off process. Correct. So now you have understood why the characteristics look like this. All right. Okay. So for levels of VGS greater than VT, the drain current ID is related to the applied gate source voltage and is practically independent of VDS, that is in the saturation region. This ID is given by a very nice
Sir, you're not audible.
times VGS minus VT bracket square. So we can say that this E MOSFET is a square law device. All right. The term K is a constant. K is a constant. and is a function of the geometry of the device. This is very interesting. So the geometry of the device will decide this particular factor K. Okay. We can determine this value of K from the geometry or from this curve basically as K is equal to ID on divided by, from this equation itself, VGS on minus VT bracket square, where ID on and VGS on are the values for each at particular point on the characteristics. So from the characteristics also we can find out the value of K if we don't know a priori. All right. So if you look at the transfer characteristics, now coming back to this figure again, you'll see that it follows this curve. Okay, let us understand this curve. So on x-axis, what is this curve? It is the transfer characteristics. Means what? ID versus VGS. Why it is called as transfer? Because ID is the output quantity, VGS is the input quantity. As again you can see that for fixed values of VDS, if I try to plot the input characteristics up to VGS equal to 2 volts, that is the threshold, the drain current is 0, and then it increases like this in accordance with our equation which we have already seen. Are you able to understand this? So this is the transfer characteristics of the E MOSFET. Guys, have you understood this? Guys,
Yes, sir.
please be very careful with this.
Yes, sir.
Okay, then how does a P channel characteristic look like? Let us see that. Let us see what is the construction of the P channel and then subsequently the characteristics.
जो ये क्लियर पूछो आगे पीछे मिला कर 30 होगा ना?
Yes.
किसे कुल 15 पेज तो ये
Yes.
आगे
Anyone having any problem?
कुल हाँ એવું જ કહેતો છે.
तो फिर
Guys,
सर अवस्था क्या नहीं एक्स्ट्रा
guys, any query?
અમે જે
Any
કાઢો
doubt?
છે
कितना गाड़ी
Somebody is talking.
એક ને બે ગણ છે ને બે
Guys, somebody is talking. I mean, is this a query? Students.
No, sir.
7 8
कुल 15 पेज मतलब तो
પણ જો ક્વેશ્ચન 5 ક્વેશ્ચન આપ્યો છે 10 માંથી 5 અટેમ્પ્ટ
ये
કરવા
क्या हो रहा है?
તો બધામાં આવી જ જાય ને.
What is happening there?
કેટલા માર્ક્સ ને એ બતાવ્યું નથી કેટલામાં કેવી ઇક્વલ માર્ક્સ પણ ઇક્વલમાં બી કેટલા અનમોલ દીદી
Guys, somebody is speaking like that. They are gossiping.
20 માર્કનો એક ક્વેશ્ચન
सर किसी का माइक ऑन है.
હું તને બતાવું છું ને
तो उसको पता भी नहीं है कि लेक्चर चल रहा है क्या? क्या हो रहा है ये? That indicates how attentive you are. Really surprising. Okay, let us not waste time on that nonsense. Okay, so this is the construction of the P-channel MOSFET. As you can see, the roles of the regions are just reversed. We have the N-type substrate. We have the drain, which is P-type, source also, which is P-type. And interestingly, you will have to connect the positive here to the source, negative to the drain. And VGS also will be negative. So VGS will be negative in this situation. Okay. Naturally, the current flow or direction of current flow will be like this once the channel is established. Once the channel is established, the current flow will be like this. Okay. Let us have a look at the characteristics. The characteristics will look, output characteristics will be similar. The only thing is that your VGS is now, yes, more and more negative. If VGS is more and more negative, drain current will be more. Okay, it is just the mirror image of the transfer characteristics of our N-channel MOSFET. Okay. All right. Now, what are the symbols? What are the symbol? How does the symbol of the N-channel look like? N-channel E MOSFET. We've already seen the symbols for the D MOSFET. So this is for the E MOSFET, N-channel E MOSFET, where the substrate is not connected to the source internally. If it is connected, it will look like this. The symbol. Be careful with the symbols. So this is the drain, this is the source, and this is the gate. Now there are alternate symbols also. This may be confusing. So many times people follow very simplified symbols. There is alternate symbol. Simply like P-channel device symbol called as PMOS, and as you can see, So this is for SS which is not connected to the source internally, or a 4-terminal device. This is for a device whose source substrate is connected to the source, and a simplified symbol like this. So this is your NMOS. This is the preferred symbol. Please understand these symbols carefully. By the way, why do you have a gap over here like this? What does this signify? What does this gap signify? Students?
So which gap?
I've already marked it here in symbol. This gap, the one
So
with
disconnect.
yes.
It is connected. It is connected to the gate.
Why is there a gap?
Sir, SiO2 substrate.
Exactly. So this actually indicates the SiO2. So of course there is a lot of meaning for the symbols. So if you change the symbols, the meanings also will change. All right. So as we have already said, we have introduced the concept of overdrive voltage. Now, just to go into a little bit details about the regions of the device. So if we catch hold of one particular curve from the output characteristics, we see that it has started leveling off. The current has started leveling off at VOV. What is VOV? It is VGS minus VT.
Minus V.
Remember this. Okay? And there are two distinct regions. In fact, three regions. Again, just like our bipolar junction transistor. This region where the drain current is not dependent, is let us say is dependent more on VDS. As you can see here in this particular region, this region, ID increases if I increase VDS. Agreed?
Yes, sir.
So it behaves like a resistor. Isn't it?
Yes, sir.
So if I increase VDS, ID increases. All right. But in this region, what is happening? Even if I increase VDS above this value, the drain current does not remains constant. It does not increase, and that is the reason why this region is called as the triode region, and this region is called as the saturation region. Again, saturation region in BJT is totally different, whereas in MOSFET and FETs it is totally different. I hope you have already learned things in when you studied the junction field effect transistor. All right. Just to let us have a look at the resistance values, which is nothing but the slope. In fact, it is going to be the conductance. So if I zoom onto this for you to clearly see, so this slope in the in the triode region is called as RDS, which happens to be 1 by GDS or 1 by slope. So the resistance in this region is given as RDS is called as RDS, whereas the resistance, which we have already called as the output resistance. Okay, so how do you calculate that? We have already calculated the output resistances for common emitter, common base, and common collector configurations, right? I've given you an exercise on that. So how did you calculate that? The slope, how will you calculate the slope? Y2 minus Y1 divided by X2 minus X1. In this case, it will be, let us say, VDS2 minus VDS1 divided by ID2 by ID1. Actually, this is 1 by slope in this case, because your x-axis is VDS. So I'll just put it in a different way.
ID2 minus ID1.
Yes, I'll put it in a different way. The slope, which is 1 by R out, is given as ID2 minus ID1 divided by VDS2 minus VDS1, which is nothing but delta ID by delta VDS. So if I want to estimate the output resistance, what should I do? Now this is looking exactly parallel, but in practice, so this is looking like it's actually parallel to the x-axis. So what do you think will be the value of RO in this situation here? What will be the value of RO?
It will be 0.
Really? 0? This delta ID is 0. Delta ID is 0 divided by, there will be some delta VDS, which is non-zero. If I take the 2 points, let us say here and here, okay, delta ID will be 0. So R out will be what?
Infinity.
Yes, delta VDS by 0, which is infinity. So for this ideal device, our output resistance is infinity. So we have an infinite output resistance. In fact, if you compare this with a current source, how does a current source look like? We've already seen this. This is a current source. So what is the ideal current source look like? This output resistance is what?
0.
Come on. Infinity. Isn't it? If it is a voltage source, don't seem to practice.
This will be 0.
Yes, this R out should be equal to 0. So this is an ideal current source. This is an ideal voltage source. So what do you see from here? The MOSFET looks like it is a
Current source.
current source, and we have already said that it is a current source. If you remember yesterday's discussion, we said
Yes,
that it acts like a current source. So things should now start catching up as per the jigsaw puzzle. Okay. So I hope you have understood today's session. Any doubts, any questions? We've already exhausted the time. Hello, guys.
So you will.
If there are no questions,
No, sir.
okay, then we'll stop here for today. You should keep on revising the concepts. Now, this is very important. All right. Thank you.
Thank you, sir.